Assalamualaikum and hi everyone, this is Dr. Shazira. In this video, I'm going to show you how do we solve a system of linear equations using Jacobi method. Alright, consider this example. We have a system here and then the question is solve the following linear system using Jacobi method with the initial guess, initial value of x is 0. So if you see x not equal to 0, it means this part here, it means x1 at k equal to 0 is 0, and then x2 not also equal to 0 and x3 not equal to 0. Okay, stop the iteration when the maximum of the difference between two consecutive x for x1, x2 and x3 is less than 0.05. Okay, so maybe you want to add here. Okay, so we assume we use 2 decimal places in the calculation. Use 2 DCP in the calculation. Alright. So before anything, before we proceed with the Jacobi procedure, first we need to make sure the coefficient matrix of our system, means the matrix A, must be strictly diagonally dominant, SDD matrix. Okay, because that is the condition for a matrix A in order for the Jacobi method to converge to the correct solution. Okay, so what is the strictly diagonally dominant? How do we identify? It is pretty simple. Okay, you can see in the definition 2.4.1 here, it says that a matrix A is strictly diagonally dominant if we can show for each of the row that we have in the matrix A, we are checking whether AII, it means for the row number 1, you are checking is it A11. The absolute value of A11 is greater than the summation of the absolute value of the rest of the elements on that same row. Okay, if you satisfy this condition, meaning that you have A in the form of strictly diagonally dominant STD matrix. Okay, and if we take a look at this example 2.4.1 here, okay, so assume this is your coefficient matrix, all right, and then for row number 1, okay, row number 1, the diagonal element is 3. So in terms of absolute value, we are checking whether the positive 3 is greater than the summation of, in terms of absolute value for 2 here as well as 0. Okay, so we have positive 3 is greater than 2 plus 0. So we satisfy this condition of SDD here. And then for row number 2, the diagonal element, the AII is at A22. Okay, so we are checking the positive of negative 5, which is 5. Is it greater than the summation of 2 here and then 1 here in terms of absolute value? So we can see 5 is greater than 3, so we are okay with row number 2. And then lastly, for row number 3, the diagonal element is 7. So we are checking for, is it the positive of 7 is greater than the summation of 1 and 2 here in terms of absolute value. So we have 7 is greater than 3, so we are okay with the condition for the strictly diagonally dominant. So we say that the given matrix here is an SDD matrix. Okay, that's how you prove or to show that you have a strictly diagonally dominant matrix. Okay, it's very simple. Now back to our problem just now. Okay, so given the system in that form, therefore if we take out our A, initially our A is 1, -3, 12, 4, 1, -1, 2, 7, and 1. Okay, so is this SDD matrix? Okay, if it is SDD, then this guy here, the diagonal at the row number 1 should be greater than the summation of 3 and 12, which is not in this case. Okay, the same thing for row number 2, the diagonal is 1, so it should be greater than 4 plus 1, which is also not the case here. And at row number 3, 1 should be greater than 2 plus 7. So clearly, this is not an STD yet. Okay? So what do? We rearrange rows. Okay, swap rows here and there so that we can form an SDD matrix. Okay, so for this one, a new here. So basically, we are looking for, the elements, the greatest element in terms of absolute value at each row. So we have 12 over there, 4, and then this is 7. And rearrange the rows so that the 3 values that you have in the box fit the condition for the STD. Okay, so we have 4, 1, -1. Okay, because 4 is greater than 1 plus 1. And then we have 2, 7, and 1. And lastly, 1, -3, and then 12. So A now is an SDD matrix. Alright. So therefore, our B, okay, also affected. B need to be changed as well accordingly. So we follow the equation in A. So we have 3, 19, and 31. Okay, that's our A and B, new A and B. Okay, so next in the Jacobi, so once we have confirmed that we have an SDD matrix, okay, so next we want to write the formula. Okay, write the Jacobi formula specific for this system that we have in the problem here. Write the Jacobi formula. Okay, so we can see at the first row, okay, A here, okay, it means that we have AX equals B, okay, at the right side here. So we know that at the first row, we have 4 x1 plus x2 minus x3 equals 3. Okay, so if we isolate the x1, therefore we have x1 equals 3 minus x2 plus x3 over 4. Okay, that is the formula for the x1. And from the second row, we can see that we have 2x1 plus 7x2 plus x3 equals 19. And then from the second equation, we isolate x2. Okay, then we have 19 minus 2x1 minus x3 over 7. Okay, and at the last row, we have x1 minus 3x2 plus 12x3 equals 31. Okay, so therefore we have x3 equals 31 minus x1 plus 3x2 over 12. Okay, but in the Jacobi, since this is iteration method, so we need to write down the iteration notation. Okay, so at x1 here, we put k plus 1 to denote the iteration number, and at the right hand side, it depends on the value of x2 and x3 at the previous iteration. So all the iteration notation at the left side should be in terms of k plus 1, and at the right hand side, that should be in terms of k. Okay, That's the formula for the Jacobi, specific for this system. Okay, and given to us, okay, given by the problem, the initial value, okay, the starting point of x1, okay, at k equal to 0. Okay, so this is 0, x2, 0 is also 0, x3, 0 is also 0. So it depends on the problem. Okay, so you just follow the value that is given to you. All right. Okay, so next, I'll show you maybe one manual calculation, and then after that we will use the calculator. Okay, so I'm going to put here the manual calculation. Okay, sample of manual calculation. So in the manual calculation, we start with k equal to 0. Okay, normal procedure in any iteration. So we start with k equal to 0. So see, when k equal to 0, we calculate, all the value of x1, x2, and x3 by looking at the corresponding formula. Okay, so for the x1, so at the left side we have x1, 1 because our k is currently 0. So k plus 1 here will be 0 plus 1. Okay, at the left side we have 3 minus x2, 0. Okay, plus x3, 0. Okay, over 4. And we know that somehow x2, 0 is given to us as 0, and x3, 0 is also 0. So what's left is just 3 over 4, which is 0.75. Okay, so that is your x1. And at this stage, k equal to 0, you also need to get x2. So at the left side, you have x2, 1. So it is equal to 19 minus 2x1, 0 minus x3, 0 over 7. Okay, so we put x1, 0 as 0, x3, 0 as 0. So we have 19 over 7 equivalent to 2.71 in 2 decimal points. Okay, and lastly for the x3, x3, 1 equals 31 minus x1, 0 plus 3x2, 0 over 12. Okay, so we put x1 is 0, x2 is 0, so we have 31 over 12, which is 2.58. Okay, so at every stage, at every iteration, you need to compute your x1, x2, and x3. And to decide whether you should continue to k equals 1 or whether you can stop, so it depends on the error. So we calculate the difference between your current x with the previous x. Okay, so currently we have x1, 1. Okay, so previously, which is given to us, is x1 at k equal to 0. So we have, in terms of absolute value, so we have that. So this is 0.75. So similarly, for the x2, we also compute the error for the x2. Okay, current minus previous, so we have 2.71 minus 0. So this is 2.71. And then lastly, for the x3, we have 2.58. Okay. Okay, so now you need to check, out of these three, which one is the maximum. Okay, so the maximum error here is 2.71. So this value 2.71 here is still, way greater than 0.05. Okay, the epsilon that is given to us in the problem here. Okay, so we need to stop the calculation when the maximum error is less than 0.05. Okay, but currently the maximum error is 2.71. Okay, so it means that we need to proceed with k equals 1. Okay, so you repeat the same process. You find x1, but now it is 2. Okay, because you have here k plus 1. So currently you are at k equals 1. So at the left side you will have x1 2, and then you find x2 2, x3 2. Okay, and so for example for the x1 here, so when you plug in k equals 1, so here you have x2 1, and here you have x3 1. So those value, the value of x2 1, x3 1 comes from the previous iteration. So you are going to put 2.71 and 2.58, okay, at the location for the x2 and x3. Okay, so similarly for the x2 and x3, the calculation for x2 and x3 here. And then after that, you need to check the error again, okay, for the x1, x2, x3, and take out, okay, which one is the maximum error, and then see whether it is less than the given epsilon. If it is not, it means you need to proceed to k equals 2. Okay, so that is the basically the manual calculation. So in the exam, okay, you can speed up the calculation by presenting your answers in the form of table. Okay, so in the table form we have the column for the iteration k, and then we have x1 k, x2 k, x3 k, and then we have the error, so x1 minus x1, but here is at k, and this is the previous, x2 k minus x2 k minus 1, okay, current minus previous, and this is x3 k minus x3 k minus 1. Okay, so when k equal to 0, so we put the value from the problem, okay, the initial value given by the problem, that is 0, 0, 0. And currently here we don't have any error. Okay, and then just now from the manual calculation, when k equal to 0, basically you get the x1 1. So in the table, you can fill in up to k equals 1. Okay, so the value just now is 0.75, 2.71, 2.58, and the error is given by that. Okay, so the maximum error is still greater than epsilon, so we have k equals 2. So now we want to use the calculator. At each iteration you are basically referring to the same formula of x1, x2, and x3. It's just that you change the value, okay, to be the previous value at the previous iteration. So in the calculator you don't have the add subscript 1, okay, you don't have that kind of button in the calculator. So we need to represent our unknowns with something else. Okay, so I'm going to assume here for the x1 we are going to use a in the calculator, x2 we represent as b, and x3 we assume as c. Okay, so it means in your calculator you are going to store 3 equations correspond to x1, x2, and x3. Okay, so the first one is your equation of x1 just now. So this one here. Okay, so we have 3 minus, so in terms of a, b, and c, so we have now 3 minus b plus c over 4, right? Then equation number 2, we want to store 19 minus 2a minus c over 7. And lastly, we put 31 minus a plus 3b over 12. Now, let us see the calculator. Okay, now we want to put the first equation. Okay, so we have the fraction. So at the top we have 3 minus b. Okay, so alpha b, okay, plus c over 4. That is the first one. And then we have another equation, 19 minus 2a minus c over 7. And then lastly, 31 minus a plus 3b over 12. Okay. All right. Now, looking at the table here, so now we want to compute the k equals 2 here. So we want to compute for the x1. Okay. So in the calculator, the formula for the x1 is 3 minus b plus c. So you go back to the first equation that you have stored just now. Okay, this one, and then you press the calculate button. The calculator will ask what is your b that you want to use. So remember your b is actually your x2. Okay, in the calculation. So x2 that you will put here is the the previous value of x2. Okay, so you are going to put this guy here, 2.71. So you put 2.71 and then equal. And then what is your c correspond to your x3? So we have 2.58. Okay, and then that is the value of x1, 2. Okay, k equals 2 at the third row here. So in 2 decimals, so we have 0.72. Okay, and now for the x2, we need to use the second equation. So you go back to the second equation here, press the calculate button. What is your a? A at the previous iteration is 0.75. Okay, and then c is your x3, which is 2.58. So in 2 decimals, we have 2.13. And for the x3, so you find the third formula, 31 here. Press the calculate button. So your a is 0.75. And then your b is your x2 at the previous iteration. So 2.71. Okay. And then you get this value, 3.198. So in terms of 2 decimals, so we have 3.20. And then you can check the difference between 2 consecutive x. So you are basically check the absolute of 0.72 minus 0.75. So you have 0.03 here. And then the error for the x2 is 2.13 minus 2.71. Take the absolute value. We have 0.58 and then 0.62. Okay, and then to decide whether we should have k equals 3 or not at the fourth row here, then we need to see in terms of the maximum error out of these 3 here. Okay, out of the 3 error. Okay, 0.03, 0.58 and 0.62. So the maximum out of those 3 is 0.62. Okay, but this guy here, 0.62 here is still greater than 0.05. So we need to have k equals 3. So similarly, okay, for the x1, you will find the first equation in the calculator and then press the calculate button. But now your value of b is 2.13. Okay, your previous x2. And then for c, okay, which is your x3, so you are going to put 3.20. Okay, so on so forth for x2 and x3, and then you check for the error and then decide whether you need to stop or not. Okay, by looking at the maximum error and see whether it is already less than the given epsilon. Okay, so for this problem here, cut the story short, you are supposed to be stopping at k equals 5. Okay, so this point you have the value of x1 is 1.01, x2 is 2.0, and here is 3.0 with the error of 0.01, 0.01, and 0.01. Okay, for this example, it is coincidentally, the error here are all the same. Okay, but for different problem, it may not. Okay, but the point is, okay, you need to look for the maximum out of these three, and you can see for this case the maximum is 0.01, so it is already less than 0.05. Okay, so we can stop here. So the last conclusion would be to write down our x1, because this is our intention at the first place, okay, to solve for x1, x2, and x3. So the x1 is approximated to the latest x that we have in the table, okay, in the calculation, which is approximated to x1 at k is 5. Okay, so this is 1.01, and x2, okay, is also at k equals 5. So this is 2.00, and x3 is approximately x3 5, which is 3.00. Okay, so this is the process of Jacobi. Okay, so in the exam, just use the calculator to speed up the calculation. Okay, but you should know, at the first place, you should know, how this thing works manually. Otherwise, you cannot relate, with the equations that you have here in your calculator. So that's it for the Jacobi. Again, first of all, you need to make sure your matrix A here is an STD matrix. Okay, if you forgot to check this, okay, if it is not SDD, then the effect would be on the error here. You will not converge to the solution, meaning that the error is getting bigger, okay, and you are not converging to the right solution. So remember, before anything, you must make sure your matrix A is an STD matrix, okay, so that you have a converged situation at the end of the calculation. All right, so that's all for the Jacobi. Bye bye. Thank you so much.